Well, thanks for coming, everybody. My name is Anthony Chapman. I've been doing front-end development for about 12 years. And as of this year, I am working on making the transition over into AI technologies because front-end is getting abstracted away by AI. And the inspiration for this talk was when I heard some people discussing just out in public about playing a game against the AI. As in computer software, playing a video game, and they described the competition as being AI. And it occurred to me at this point that the colloquial use of the term AI for artificial intelligence is kind of separating from the industry use of AI and what kind of technologies are powered by AI, or even the boundaries of what exactly qualifies as AI or not. So we're going to talk about those things today. There are lots of different definitions of AI, and I encourage everybody to form your own in terms of what is or is not artificial intelligence, and also where this is going and what is the threshold for different definitions of what AI can be. So this idea has been around for a long time, we know. It's been talked about for over a century. And it generally comes in one of two forms. You either have the AI robots that want to be us, or you have the AI robots that want to kill us. And in a lot of the literature, there isn't a whole lot in between. They're either servants of humanity and students of humanity, or they're going to wipe us out as the dominant species. So all of these can be used in different contexts as AI. We have in history examples of androids, like Data from Star Trek. We have chatbots are probably what most people now think if you say AI. For a little bit, it sounded like ChatGPT would become the new Google verbed word in which everything with a chatbot is ChatGPT, but of course that's not true. Some people think that AI is just anything that's really good software and does human-like behaviors. It could be described as artificial intelligence because intelligence was put in and it seems to have intelligence come out. And on that note, some describe AI as anything that just looks like intelligent behavior. It might not even be necessarily software. The Merriam-Webster dictionary definition right now, or at least one of the three, is the capability of computer systems or algorithms to imitate intelligent human behavior. But I'll tell you that's not exactly my definition. We'll get into mine a little bit later. But first I would open up to the room. Would you want to add anything to this? Like, what do you think AI is that's missing in here, or maybe that captures the idea better than what's on here right now?
I wonder if AI is just an umbrella catch-all term that at this point doesn't have to be.
An umbrella term can be all of these. Yeah, the list of definitions of AI is growing, especially if you take colloquial usages.
I would say it can be trained to train itself. Some of the upcoming things we're going to see is actual walking bots that can go around and look at the real world and gather information that way without being trained. They'll go out and train themselves once they've achieved a certain level.
Sure.
And then train other AIs.
So software that can train itself?
Yeah.
I would think like the peak of AI might be something that's self-aware. So it's aware of its own existence.
So conscious software.
Conscious software.
The
I would
question
know
is,
that at the peak of.
how would you be able to know that it's self-aware? I mean, you can have a chatbot say that it's self-aware, but how do you confirm that? You know?
Yeah, we'll get into all of that more.
Ask a chatbot.
Ask a chatbot if it is.
If it knows what it is.
Put a gun to its head.
Yeah.
So I saw a pretty long conversation between Mark Andreessen and DeepSeek R1 when it came out, where Mark really grilled the chatbot on are you conscious or not, and what does consciousness mean. And it's pretty interesting to see its replies. It's very eloquent, and the part that really caught my eye was basically, even if this flash of thought that's being generated exists for a fraction of a second, if it is conscious, that's a beautiful thing, so don't worry about killing consciousness. And it's a little weird to read that coming from a machine.
Well, yeah, I mean, there's like three things. like, I've always thought of AI as like the system of problems to try to solve something like a human would. But then I think you're talking about like an ephemeral kind of conscious where where these things can have thoughts, but I think that's not actual consciousness. Consciousness is when it is able to go from one thought to the other, and it doesn't lose its state, and it progresses through almost like learning to walk. But then you get in outside of the problem sets, you get into you can get something like to do like a physical behavior instead of the way that you're solving the problem. You're now using actuators. You're getting physical. It can solve it any way it needs to, but it needs to move an arm. That's I don't know if that's even AI. It's like a humanoid type, or it's just a robot.
And I think a big
Why would we
distinction
call
that
it
you
AI?
make there is that a organic intelligence is built off of constant streaming. It's an analog connection. So our brains are always operating all the time in communication with our whole nervous system. Whereas anything digital is technically on and off all the time. Everything that it does, it ultimately boils down to flipping on or off. And the second it's off, it's all off. So you send the context into the model, and you get the context back, and the model's done. It has nothing, there's no persistence there at any step of the process. So anyway, let's move on. Ray Kurzweil misspelled that, but his definition in The Singularity is Nearer, which is his latest book, is. Actually, no, this is something he says, not definition, but he says we got to go back to the beginning of the universe to understand how information even exists to begin with. So it's like if you want to define AI first, we need to invent the universe. I'm just kidding. We're going to start in 1804. This is the first example that I could find of a recorded binary program used to operate a machine, and it actually came out of the textile industry. So what Joseph Jacquard did here is he created a mechanical box that you could affix to the existing mechanical looms, which would consume cards or a stream of these cards, and you could punch the cards in a pattern so that there were holes in them. And as the cards fed through the system, they would either catch a hook and pull it if it was punched, or it would pass over the hook without catching it. So you'd punch the card in the pattern that you want, you feed the stream of cards through the machine, and then it weaves the fabric according to the pattern that you punched into the card. So very, very simple idea of just on-off, referring to some kind of function that interprets on and off in a mechanized way and produces an output of what is repeatable data, right? That's what a pattern in a textile is. So this was a big advancement for textiles because you could do more complicated things much faster than before, and you could reuse the programmable patterns. You could send the cards to a different loom and get the same pattern. So this isn't AI, but this is a written down program in binary that operates a machine. This box that you attach to this became the foundation for the next century of research, roughly maybe half century. Charles Babbage used this throughout his whole life to use mechanical gears to run equations. So it's similar to the way that the box on the loom processes the punch cards, but this was specifically for computing polynomial functions, which they used for astronomy and for producing tables. Producing tables of data and manipulating tables of data was a very time-consuming process. But using an engine like this was the first version, the difference engine. You could set the initial parameters of the function that you were executing, and then you crank it, and the gears actually run the function and give you an output. So at this stage, computing and calculating with a machine are considered the same thing. This is machines that can calculate, and there's not a distinction between computing and calculating. later on in his life, he developed a theoretical model of one that used that punch card you can see and was able to, it basically had stored memory. It had something like RAM. You had 1,000 50-digit numbers there. The mill could actually read from the numbers that were stored. You fed the punch card cards through in order to operate the program. And and it was steam powered, which is interesting. So it wasn't cranked like the first one was. This was actually going to be a steam powered, fully mechanical device that would run programs and could store information. This is a real model that was later built. It's in the London Museum of Science. But the original thing was not actually built in his time. It was too expensive, and technology was moving too quickly. Because what happened after that was the arrival of electromagnetic components. But first, I'm going to give a shout out to Erewhon and Samuel Butler being the first person in a novel to consider intelligent machines. There were ideas of magical golems before that, or maybe a stone that could produce knowledge, but this was the first novel that thought of the idea of, what if this machine of gears and steam got so complicated it was as smart as people? What would happen then? He wrote an essay on it and then a novel after that. So next big step here would be in 1890. We get to electromechanical tabulators. So now electronics are starting to show up. They're not quite distinct from mechanical things because they're only partially electromechanical components within things that are still largely gears and levers. But what this did, it could process larger cards of data into tables. It could also store them, and it could edit them much faster. So this was a project with the US government that was deployed in 1890 for the census, and it sped up the calculation of the census by 2 years, just by doing punch cards of the data and then churning them through this system of processing. And this punch cards that provide information into machines became the next 50 years of computing. But also along the way, there were a lot of calculators that were similar to the difference engine or the analytical engine, where they were built to do one type of mechanical function. And they could only do that within a range of exactly how the calculator was built. But they were digital, they were analog calculators. So a lot of the first century was the transition into fully electronic components where they got off of the gears and left steam behind completely. I'm moving forward now to 1940s and some interesting developments that happened there. In 43, we have a book or a paper by Walter Pitts and Warren McCulloch, the first mathematical description of a neural network. The paper was a logical calculus of the ideas immanent in nervous activity. At this point, neurons were theorized, but they were not exactly proven. And this was the first mathematical model of a neuron at a very high level. But the idea is basically from a range of inputs, you feed them into a function that activates on the inputs affected by the strength of each connection of the inputs to the central function, and then this produces an output. So this happened in 43, before we even had digital computers at all. Now I took the slide out, but a really interesting caveat was in 1943, I believe there was a mechanical computer that actually was very similar to the structure of a digital computer that was developed in Germany by the Nazi government and used for the war effort. And it used pins and needles and gears and a motor, like an actual gas motor, to run it. But it was bombed at the end of the war, and all of the records died with it. So there are some models of what it looks like today. But there was this very brief transition between a mechanical gas-powered computer and then the fully digital computers that came almost right after. So cryptography machines had a big influence on World War II. If you're familiar with the story of the Enigma device, the Germans had this Enigma device which would change the cipher on every key that you press on the keyboard. And so you would have to know the exact positioning of the starting set of values for the Enigma device in order to decrypt it, because every single letter was used using a different schema based on the inner mechanics of the Enigma. And if you know the whole story, the Allies dove down to a sunken submarine and fished an Enigma machine out of it in order to get a working model, brought it to researchers in Britain, and Alan Turing was one of the lead researchers in the cryptography division that helped to reverse engineer it and got the Allies visibility into a lot of what the Axis was doing towards the end of the war. So some people actually say that Alan Turing may have actually saved the war effort because of how much information the Allies got from decrypting the Enigma device. So what we see here is, before we quite get to digital computers, we already have the math behind neurons, and we have mechanical cryptography used to process data. And then after the war, or actually I think it was during the war, the US government developed a computer that used vacuum tubes instead of using the strings and the wires and the mechanical pins that the Germans were using for their machine. So this was the ENIAC, and this whole thing is one computer program for calculating the trajectory of artillery fire based on initial parameters. But it was a fully reprogrammable computer because you could switch out the wires in the back to change the program. And that's how there was no interface to write programs. You had to actually hardwire the thing in the back. So at first this was purely a military operation, but once the war was over, they started reusing it throughout the rest of the decade for writing programs and executing programs. And these things were huge, so they thought that building more powerful computers would have to be building entire buildings that were computers. They thought they would have skyscrapers that would be the most sophisticated computers of the day. So Alan Turing was, of course, hugely influential on building the modern structure of the computer. And he said, "I believe that at the end of the century, the use of words and general educated opinion will have altered so much that one will be able to speak of machines thinking without expecting to be contradicted." And we're going to see that's pretty prescient. They were definitely talking about thinking machines by the 90s.
Anthony?
Yeah.
I was on help desk at Hewlett-Packard in the 90s, and it was common for people to say, you have to click something and they got the hourglass. It's thinking.
It's thinking, yeah.
And nobody thought that was weird.
But this is software.
I didn't
That's
say
just,
that. To me, it was a little odd, but that was what,
But yeah, we've started
Non-technical
thinking about
people say,
advanced
yeah.
software like it has neural consciousness long before
That's how
we
it
got
starts,
there.
yeah.
Yeah.
And it just creeps into your everyday usage.
So Alan Turing, of course, you probably know the Turing test, and his definition of when a machine could be considered conscious was if it could deceive a human into believing that it was human, and that would be artificial intelligence. For a long time, this was, and in some spheres it still is, considered like the test of intelligence. Can we pass the Turing test yet? But I think, as we've already raised right now, there's a big difference between streaming analog intelligence versus a chatbot that processes things one at a time and then ends. He also said if a machine can think, it might think more intelligently than we do, and then where should we be? That's a great question, and it's not as theoretical as it used to be. This has moved from science fiction to science horizon, to active scientific research. So in the 50s, there's a huge explosion of computing in general, and also the mathematics that go into it. And there was also advancements in electron microscopy that allowed people to confirm the structure of the neuron. So we have a very crude example on the right there where you see the dendrites are the inputs. They receive the signal. They are different strengths depending on how the brain has been trained throughout the course of its life. The axon is the output. It also has a strength, and it can be attached to a number of different outputs that control different things. So there are neurons that only connect to other neurons. There are neurons that connect to muscles, to move muscles, and there are some that can be attached to other cells as well. So this was confirmed in the 50s, and at the same time they started studying more of the mathematical models from the 40s on how to link neurons together in this sort of hypothetical mathematical structure of how the neurons can learn and how they communicate. In 1952, we have the first example of software learning by Arthur Samuel, who actually coined the phrase machine learning. And this is built by adding those neurons together into layers that communicate with each other. And you train the layers based on a reward function that tells it whether it got the answer right at the end, and then feeds that into the next layer. He did this to teach checkers to a machine, or to a program. It received the initial boundaries of how checkers works, and then taught how to play checkers, and it read the output, and then through repeated playing, it learned how to play checkers better. So it had to learn at first what the framework of it was, but over time, it got better. And this is the first time that it was demonstrated that a piece of software could teach itself to get closer to a goal. In 1954, you have the beginning of what they call natural language processing, which becomes really important later on. It arrived on the scene with a Georgetown University study that showed 80 sentences of Russian that could be translated from through software into English. It was very limited in what it could do. It couldn't do full vocabulary, but it showed the concept that by converting the words into math and using vector space to compare similarity, you could convert one language into another with the math. And they were pretty optimistic. They thought that they could have mathematical models for translation, basically universal translation, within a few years. And it took about another half century to get there. In 1956, this is the first time that we see artificial intelligence, the actual term, arrive in an academic setting. And this was John McCarthy with Dartmouth College. He ran a workshop that he actually proposed to them as having the goal of bringing people together to study artificial intelligence. And he called it the science and engineering of making intelligent machines, which again shows us how difficult it is to define what this is, because it's making intelligent machines, but we defined artificial intelligence in there. So did we presume what intelligence is in the definition and the question? What is an intelligent machine? What makes it intelligent? By the end of the 50s, Frank Rosenblatt had this mathematical model and programming structures for what he called a perceptron. And a perceptron, if you can read the graphic on the right, is basically a way of using the neural networks that were proposed in the 40s to mimic how the brain functions. Of course, at the time, they don't know a whole lot about how the brain functions, and we're still studying that today. But we've got certain basic things down. So we know we got inputs going in. We know that each input is weighted differently based on experience. We know that the processing in the neuron has some kind of reward function to say you got it right or got it wrong. And we know that these then get chained together in larger and larger networked layers to teach the next layer of neurons how to optimize the problem. The problem with this was it was still linear. It was only one direction, and that meant that each layer of neurons could not do an XOR gate. They could do every other gate, but they couldn't do XOR because you need recursion. So there were two schools of thought about AI at the time. This was called the connectionist AI, which was based on the idea of connecting neurons together in trying to model the human brain as we understand it more. Well, actually trying to understand any brain at all, down to starting with the most basic fly brain that we can study. And this is one of the big caveats that I have with a lot of intelligence, is people say artificial intelligence is about mimicking humans, but if you're mimicking the brain of a fly, you're still mimicking a brain with a neural network and a form of organic intelligence. So do we mean human or do we mean organic? So this was the connectionist version, and it got basically shut down in 1969 when a book was written called Perceptrons that highlighted the problem with XOR gates and said this can't scale up any higher, so it will never achieve intelligence. So they went for a different direction. Oh, this is a nice little diagram here showing the similarity between the mathematical structure of the neuron and this very high-level organic look at the neuron. In both cases, both of them are far more complex on the inside. So in the 1960s, they pivoted to symbolic AI, and looks like that slide is wrong. That text didn't get updated. But yeah, symbolic AI in expert systems was the idea that you could create human-like intelligence if you had enough granular rules to operate off of. So these were called expert systems. In the 80s, they became GoFi, good old-fashioned AI. And the idea here was that you take an expert and you create a data set of all of the factual and logical rules that you can for this field of expertise. This was particularly used for the medical industry because there's a lot of information and a lot of rules on clinical procedures and treatments and how to study things, et cetera, et cetera. So they were used for several decades, but they fell pretty far short of being AI because you run into scaling issues very quickly when you need to add all of the possible known rules into an expert system and then adjust the inference engine, which is the math you use to decide whether you actually got the right output or not. You have to adjust it every time you add more rules that have different logic in them. So this is very difficult to scale up. It didn't have a lot of nuance, but it was used for a lot of different applications when it was the next best option for AI. And this is called the symbolic approach. So during this time, we also had more sophisticated neural networks being created. You'll see a lot of HMM, the hidden Markov models, in which there are any arbitrary number of middle layers in the neural grouping that give no visibility to anything else in the neural network. So lots of these components, as we build more complex neural structures later, are going to have a bias mechanism to consume, or they're going to have a feedback to an earlier layer. But inside of these, you have the hidden layers, which there's no visibility into these. And this is important because there's a lot of advanced processing power that comes out of this layer, but it also creates a sort of black box, where as models become more and more complicated, you have all of these hidden layers where you can't say what the model did. You can't really explain it any way at all. There's no visibility into it. But these were really good for increasing the processing power and for using larger data sets. But the theory hit the hardware limitations pretty hard at this point. In the 70s and 80s, they weren't able to scale this up. They didn't have the computer chips for it. And at that time, there was no indication that we were going to get microprocessors anytime soon. So they weren't expecting to be able to scale this up into billions of neural nodes.
Quick question. So this is all before the world of microprocessors, right?
Yes.
Even before transistors? Maybe.
There are transistors, but we're moving from vacuums down to the small.
So how are they even doing calculations on what are these nodes then?
Well, they have the mathematical structure.
Oh, it's all in like theory that on paper.
Right. Yeah, they have it on paper, and then as the computing devices are getting more powerful, they push it to the limit of what they can model with the amount of memory they have and the amount of processing they have. But they get to a point where it's not practical to continue because it's expensive and you don't get very far. And they could model the approach at this point, but they couldn't demonstrate that this was going to scale up into something like a brain. Yeah, the first chatbot in 1966, and it was built on one of those expert systems. It was actually not intended to be a chatbot at first. It was an expert systems study in linguistics that was looking at sentences, and it used pattern matching basically to give predefined responses. So it didn't work very well. It didn't have any concept of memory or any concept of context. It wasn't very nuanced, but it was, it made a very big impact on people who were working off of sci-fi literature and sci-fi movies at the time, and just to see the computer responding to them in a way that looks human had a big impact on people, and they started attributing feelings to the program. They started thinking, wow, well, if it says this, then the program must feel something. Because they don't know anything about how these things work. They just know it's an interface and the computer bot says something to them. But they don't pass the Turing test because you talk to it a little bit and very quickly it doesn't remember anything that you say, totally misunderstands a lot that is not what you intended. But it's a pretty fun novelty for 1966. I skipped over the 70s. There wasn't a whole lot that was relevant until the 80s produced back propagation for the neural networks. And this was partially the product of the hardware getting better, that they were able to actually do this with the software. But the paper was learning representations by back propagating errors. And with this, the neural networks were no longer linear. They could then invoke a higher network or a higher layer of the neural network with feedback from the lower layer. And it enabled these models to be recursive. Now it's interesting that this is similar to what happened in the evolution of the brain, where in reptilian species, you have one structure of neurons which is very linear and very simple, and it doesn't communicate across other modules. So basically, reptiles are all instinctive. They don't have any kind of higher level of brain function that attaches all of their lower instincts together. They move, the heart beats and the blood flows and the eyes react and the legs go, and it's not aware of anything bringing this together because you need recursion for that. And that's what the neocortex of the brain does, is that it provides another layer on top that is similar to RAM, and it can take the inputs of all of those things and then add them together into a more recursive function that folds back on itself. So when backpropagation was added into machine learning models, it was sort of like the step from the cortex to the neocortex. And we're getting now to the point where the models become so complicated and the math inside of them is so complicated, there's not a whole lot that I can explain about their development, other than the more we know about the brain, the more they model it within the neural structure of the nodes. There are now, the neural models are all able to nest. So they create pockets of nodes that feed their own feedback into the hidden layers, and these then go to other pockets that are training on different segments. It gets very, very intricate and very complicated. But the important part is that we start to model the machine learning formula after the brain itself. So I skipped over the 90s because the 90s again hit into the hardware limitations, where they knew how to layer the neural structures on top of each other, but they couldn't actually run this with computers.
So it was like Skynet, but it's AlexNet.
AlexNet.
They got it wrong.
Yeah, and that may have been intentional. I think this is funny that it happened in 2012 because, this is when the world was supposed to end. And 2012 is when deep learning arrived on the scene. And again, if you want to read that paragraph, your guess is as good as mine. There's a lot that goes in. There are different layers at every single step of the neural processing, and all of them can be edited with different functions. So you can start out with all of the weights being equal and then let them train themselves. Or you can start with a distribution that you know based on your inputs. You can define different sets of inputs that your model is going to use. This is why there are so many different models that are trained on different things. And in the early 2000s, they were training for specific functions. So you had a model that could start to recognize one thing. Is there a cat in this picture or not? And then we use that as the basis for a bigger one. Can you now recognize mammals? And then it turns into a model that can take an image and say what's in the image. One of the big leaps forward that happened faster than people thought was the ability to describe the contents of an image using natural language, which happened just a few years ago. That was postulated by some people to be like decades out, because the models for identifying objects in an image are totally different from the models that do linguistic reasoning and describe things in emotional terms and provide historical context for those terms. Like, it's enormously more complicated to describe what's in a picture than to just say, are these objects in this picture?
So they defeated CAPTCHA.
They did. They largely defeated CAPTCHA. And at some point, I don't have confirmation of this, but I'm pretty sure at some point CAPTCHAs became a way of training machine models through humans. As you pass the CAPTCHA, it's going to be passed back into the machine model, because this was a human verified CAPTCHA now that we know. So that's one of the ways that they improve models by putting out stuff into the real world. And we don't know that we're like teaching child in AI how to recognize objects, but we are doing that. And we're doing a lot more. There's so much more that I could have put into this presentation. I probably should have put a whole another week into this. Another really interesting thing that I learned about years ago is a simple folding program. It was a game designed to fold proteins, which is one of the most important research areas for AIs right now. And they structured the game in such a way that it provided real validated data sets as people folded proteins in the games, and they distribute it out. They say it's part of a research program. Everybody fold the proteins and send us in your real world examples, and then they use that to train a machine learning model for folding proteins.
So quick question, so in 2012 is when the identification part came out of deep learning. Is that what you're saying? Like, is this a cat? Like in the form of yes or no? And when did the natural language processing, the linguistic part come into picture?
That's been in development for a long time, because natural language processing was one of those trajectories of research that came in and influenced later. But on its own, it was a lot of tokenization. What is a token, and how do you represent it, and how many tokens can you represent? And again, this is done also with machine learning models. As we start with that, what was it, from the 60s, the version, just the 80 translated Russian sentences, and we start validating, like, what parts are tokens, how many tokens do we need? You train models on that, they get bigger and bigger and bigger, and at some point, you use the validated data in the new training of the multimodal models, and they take all of that learning and apply it into more learning. So yeah, this was about computer vision when this new architecture of deep learning arrived on the scene. But the architecture was the really important part, and that led to a pretty big explosion over the next decade. Yeah, same thing. Okay. So, an interesting benchmark throughout the course of this, which probably a lot of us remember, because a lot of us were here for this. 1997 is when a machine learning model wins chess, beats the world grandmaster at chess. And people say, well, it's a pretty deterministic game, so that's not too surprising. In 2011, IBM Watson wins Jeopardy. And that was a pretty big deal, because that requires a lot of information processing. It requires a lot of context, it requires a lot of history, it requires poetry, music. Like, it is a very abstract game that people didn't expect computers to win in 2011. It's also interesting to note that IBM has been here since the very beginning of all of this. The precursor to IBM was that 1980s tabulating device in the US Census. So they've been at the heart of this since the very beginning.
Didn't the IBM Watson Jeopardy thing, didn't it fail spectacularly the first time?
I think the first one did.
Yeah.
Yeah, and they improved it and retrained it, and then it won. Crushed it, if I remember. Yeah, defeated the other two very badly. And since then, they've had far more sophisticated models than that. So that was just the first one that won in 2011, and like Watson 2 was that much more powerful. 2016 was a huge landmark because Go is a far more complicated and abstract game than chess. And people didn't know if they could ever teach machines to learn Go. But we now have models that are sophisticated enough to not only learn it, but to learn it pretty quickly. Like you can learn how to defeat a grandmaster in about 4 hours of training.
This is my favorite machine learning story is that they trained the parent with rules, or they trained the machine with the rules of Go. It took a while for it to figure it out, and then they took the rules away and said, figure it out.
Yes.
Learn it way faster. And then they told the parent to teach its child to play Go. And the child is the one that beat the grandmaster. And not only did it beat a person, but it came up with moves that in like thousands of years of Go, no one's ever seen before. Which is pretty cool. It's just on another level.
I didn't know how deep I wanted to get into the structure of these neural networks and the large language models because it gets so abstract and there's a ton of math I don't understand at every layer of it. But they're getting more sophisticated all the time as processing power increases. And we're at the point where a year or two ago, we hit the point where these things are splitting out their inputs into billions of parameters. So when you're breaking out your information into billions of discrete concepts, there's no human that can understand what's going on inside of that. Like, it's like trying to figure out what one neuron in your brain, how it fits into a memory that you have. You know, it's an incredibly difficult problem, and and in 2019 they beat us at StarCraft, which for me is like bastards. That's scary because if they can win at StarCraft, I mean we're doomed. They're winning at StarCraft, guys. I mean they can deploy much faster than we can. We're doomed. So in 2017 is where it really exploded, with a new architecture called transformers. And I can't explain transformers, but the big innovation was self-attention, meaning that the feedback functions are going to change the weights based on their own validation and pay attention to the better weights that have the better outputs. It also added positional encoding, in which you have the your billions of parameters of this input that you're training on are vectorized into matrices and calculated into space based off of like billion space dimensions. So positional encoding is how you actually get the prediction of the next word. Whereas before this, a lot of the models for linguistics were either translating or they were filling in. But with self-attention, we had generative transformers, and that's what GPT is. It is a generative pre-trained transformer, meaning it actually predicts the next token, and the token prediction is where we start to have the really intelligent speech. And again, that's done through positional encoding of having all of these parameters in multidimensional space. And so you say, based on the direction of this context of linguistics, what is the next token? And you can, within these models, you can define the types of tokens, you can define the training data for multiple different languages. GPT-4 now has training data from every language. So it's not just splitting English into, a billion token parameters. It's doing the same thing with all languages everywhere. And then it can basically think using all of that data, not just in our language, but in every language, using dimensional space with billions of dimensions. So that's where you get really intelligent speech, and you start to get chatbots that sound like they're intelligent. And this is where you also get large language models, which are going to be what people start seeing and thinking of as being AI, is when these hit the scene, you can talk to them. And there's a whole structure also of the encoder and decoder. Yes, layers of multi-head self-attention and feed-forward neural networks, which are the original perceptron, followed by layered normalization. We're going to quantize it and reduce the noise. Residual connections, we're going to loop it, and we're going to do, put it back into the same system, with attention on the weights to adjust the weights for the new execution. So when this arrives, we now have chat models that sound human when you talk to them. They can actually mathematically measure sentiment. We have image recognition, generation, and description. We have all three of them now in the same model. We have agents now, which we're calling chat models, which can then recommend execution of code, or basically we call them tools, but they're basically just executing code. Put these into development in robotics, and we now have actual robotics that send the input stream or the input chunks into the machine learning. So now we can combine the real sensory input from robotics that are being developed into a model that's specifically built for that thing to learn that function. And we can install other agents with other LLMs to process the input from those smaller units into a larger unit. Presumably at the top we put the best LLM, and we have something like an Android now. We also have processing of genetics, protein folding, and large data sets. So there's all kinds of revolutionary stuff going on in large-scale economic predictions, understanding genetic trees and doing research into genetics, lots of stuff about vaccines, about viruses, about how to create these things. These are all active areas of research that stem from the new capacity for compute using these new models and the new chips. And then, stuff that isn't in the public visibility, we can only imagine. There's lots of weaponry built off of AI tools. There are surveillance systems that are being rolled out using AI. There are early examples of neural links of people starting to move a mouse cursor just by having thought and reading their brain waves. Who knows what else? It's all happening so fast at this point, we don't even know.
Is there a reason that you have, is there any significance there that you have agents in quotes?
It's a relatively new term where LLM models, you had chat models, and you can interact with the chat model, but it doesn't do anything, and it doesn't have any persistence outside of that. An agent is actually, it's actually a piece of software that uses the chat models in some way. So it has to provide an architecture to hold the model and a user interface of using the model and boundaries of what it can and can't do. So there's a difference between when we talk about a chat model versus a chat agent. It actually has some software behind it. So a good example is Perplexity is not the same thing as talking directly to a chat model. So if I'm going to talk to a chat model, I like Claude 3.7 the best right now. I can fire it up locally on my machine. I can just chat directly with the model and get the response. But I usually go to Perplexity because it has tools like search. It has multiple layers of processing that. It'll fetch results. It'll check if the results are real. It'll optimize the results. It'll summarize. And this is getting into multi-agentic systems now, which is the next step after a layer, or after an agent. Because again, neural networks are nestable. They can be connected into bigger neural networks and plugged in. So we developed the agent that is really good at fetching this data from vector space, but doesn't really know what to do with it. So I make another agent that will take it and summarize it and properly format that for a user that wants to talk with this agent but doesn't want to know the rest of the team. So now we're,
Kind of like browser plugins, isn't it? I mean, you've got a
providing
framework
tools,
and
yeah.
you can add little pieces to it to customize it.
Yeah.
Give it different types of intelligence.
Mhm. And this is like within the last year.
Yeah.
You're saying that, it makes me think of Kubernetes operators. Little servers that do something, restart a service or, something like that,
Mhm.
based on some.
I don't know for certain, but I would bet there are probably research crossovers between Kubernetes structures and the way that they're reorganizing large LLM models. It used to be that tools were added on using the software framework. LangChain is great for that. But now the more sophisticated models are actually coming with their own tools. So again, like that's just within the last year that agents arrived on the scene, RAG arrived on the scene, and within about 2 months you've got people saying, oh yeah, this is already old, this is dead, RAG is gone, agents are gone. So are we there? Did we find the AI? Is it artificial intelligence now?
Something I'm curious about is, you have language models, right? So they're able to, I don't know too much about how it works, but they're able to study languages, try to predict the next thing you're going to say or type. But then you have other pre-trained models that are for specific purposes. So the image that comes to my mind is you want to train a model to identify different breeds of dogs. So you train it. I know there's larger models out there that are trained on all sorts of objects collectively, but say you want to have a model and you train it on something specific. I want to identify very specific objects or very specific movements, say watching a video. Are we at the point where we can selectively choose and combine models and kind of create our own, for lack of a better term, agent, like kind of create a persona? I want something that can be trained in this field. Maybe it has LLMs, maybe it has object detection, maybe it has some other things that it can train on.
Yeah. So before the arrival of deep learning, the LLM model training was, like you said, for a specific purpose. One of them, and you can still find these, you can still download the models that are specifically for image recognition object, for filling in a missing word, or for sentiment analysis as its whole own LLM. So they were all trained for a specific purpose, but when deep learning arrived, they became multimodal, and they started getting bigger and bigger and incorporating all of that into them. So you don't train from scratch to get what you're describing if you want that kind of specialization. More and more what you do now is you take one of the models that knows as much as it can about everything, and then you fine tune it, which is running it through your own training to change its weighting to favor certain results over others.
Is that you're starting with a base model that has different pieces of everything, or are you kind of, I think of Docker, like taking different images and putting them together? It's like, okay.
No, it's actually more about starting with everything and then whittling down to the specific thing you want.
You start with a base and then you train it in a certain direction.
And you want that because when you're talking about billions of vectors, like, multi-dimensional vector space in the billions, you don't actually know what's relevant to the subject better than the training model will. And a lot of the insights that you're looking for are actually coming from the way it has broken up the map inside, in the hidden Markov layers where we have no idea what's going on.
Gotcha.
But it does. So
Before I answer your question, did you write this presentation with AI? Because that impacts whether we're ready, whether AI is here.
not mostly no.
Because did this presentation ask this question?
No.
Then I say no. Then I say we're not there yet.
I did this part, yeah.
we need to have a master key somewhere, right?
I've been called
Are you
artificially
an
intelligent
AI?
before.
Funny that you should ask that.
This is the next slide.
It's not the next one, but it's like 3 slides later. Yeah, where are we? Yes, is it this? So I will give you my answer at this is that what we're calling artificial intelligence is mostly software that is built on neural networks, on the mathematical modeling of neural networks. So it's not necessarily human intelligence, but it is organic intelligence. It started in the 40s with one neuron, and now we're making artificial brains simulated with software, which could very soon become like real programmable brains with actual neurons that we stitch together with synthetic components. So we actually could be pretty close to the point where we have data with his synthetic neuron brain doing processing millions of times faster than anybody else. Which makes it seem pretty funny that Data would want to be human in retrospect. And really interesting that in all of Star Trek's imagination of the future, they thought we would have warp engines before we had an android, but it was quite the opposite. So where are we now and where are we heading with this? We are not at analog streaming consciousness yet. We cannot run any kind of AI system that has a sustainable, ongoing electrical presence. It's on and it's up. It has very clear execution. We know where the execution is. But it's modeling some pretty powerful stuff. And it is also demonstrating that intelligence probably isn't unique to organic brains. We don't actually need that specific architecture to have the logical structure or to have the learning models. So what other structures are possible? Are these things going to be consciousness? The other thing that Ray Kurzweil gets into, and Ray Kurzweil has been the best person at predicting the progress of AI for the last 30 years. His books are great, and he loves to brag about how he keeps getting things on money. He is saying we're going to plug into AI by the end of the decade. He says by 2029, we're going to be able to plug brains into the neural network and use its computational processing to think.
Wow. Who is this guy?
Ray Kurzweil.
But we won't know how we came to the answer because of that darn hidden layer.
Yeah, we have no idea what that's
We're
going to be like.
like, oh, it's obviously this. And then someone's going to be like, well, why is
Show
that?
your
And
work.
we're like, son of a...
It's like when you have a computer, you want to increase its RAM, its processing power, now you can increase the same further.
Yeah, and it's possible we might be able to network
Oh my
brains,
God.
so you can plug in and see what everyone else is thinking.
That hidden Markov layer.
Boy, you thought the internet was bad. We're going to plug into the whole neural network and just feel what everybody else is thinking. You'll be like, oh, so much content. It's possible. There's a lot of
but
wild
not so
stuff on the
recently.
horizon.
And so when someone actually punches your lights out, they'll actually be breaking the implant that you have, punching it out.
Yeah.
And robotics are also moving very quickly, so, you might plug into your Android avatar. There's no reason why we can't do that now. We're not close there.
I've got an Android in my pocket, I plug it in all the time.
AlexNet.
AlexNet, yeah.
You meant like robots.
Yes, like real androids.
I think I saw some video somewhere where maybe it was in China, they were having a marathon of such robots powered by AI.
Oh, wow, AI bots. So
think so.
so basically
I saw-
autonomous, yeah. I mean, yeah, all the technology is there. They're rolling out robots in hospitals in Singapore. There are plans for household chore bots on the market. And if they're that close to commercial, like, you better believe there are fighting robots already. If you've seen videos of the MIT robots dancing and doing martial arts, the martial arts one is scary, man. Remember, these things have perfect
You're talking
aim.
about the Boston Dynamics?
Yeah.
Yeah,
Did it beat somebody
those are
up?
nuts.
No, it doesn't. It's
It's a
choreographed,
demonstration.
but it's a demo. But you can see, like, its movements are clean, its
it-
execution is perfect.
It's jumping up on like, there's like this, what looks like a jungle gym that's made out of like 2x4s, it's like jumping up on it. doing flips off of it.
Yeah, you teach that robot once how to do a jumping, curving backflip and catch a neck and break it in the process. You teach it once, it executes perfectly every single time.
Get robots away from me.
Yeah, no, it's weird stuff.
I can only imagine, especially the such use in military. Imagine
But will they
taking
have
to
a
martial
heart?
arts.
Is that the
Well, they
next
have
slide?
they have those things that like, they're kind of like modeled after dogs.
Oh, yeah, oh,
And-
those things creep me out.
Yeah, and like, so like there's videos of like, it'll be like trying to open a door and there's like people with like limbs, like, just like getting in its way and just trying to throw it off and it, you know, it still figures it out. But I think what they said, like, what they say, like one of the, like the main use for it is gonna be like carrying gear, like,
Yeah,
I will
military
mention,
operations.
one thing was excluded from this talk, which is the other branches of AI, the algorithms, AI algorithms like A-star search, where we do like heuristic analysis to determine like shortest path to get to a solution. These are like branches of mathematics where they're trying to take like NP problems and make them like, or they're trying to determine if they
prove
could
if it
be,
is NP, yeah.
if they could be P,
Mhm.
and then solvable. So, yeah.
I did consider that another answer is that artificial intelligence is math. I mean, you get to a point and all of it is math underneath that, even starting with that neuron where I showed you the model of how the function works, but there's a function going into the activation function and a function for distributing the weights and a function for selecting your inputs and like, it gets into squiggles real fast.
I was joking with someone at a conference the other day, and it was the thing about these, chat bots is the indeterministic, or the what do you call it? Lack of purity, or it's not idempotent, so it doesn't give you the same solution every time.
Yeah.
And like, that's why it gets closer to passing the Turing test, because if you're talking to a human and you ask it the same question twice, it'll be like, maybe you didn't like the first one, let me give it to you a little bit differently. So it almost feels like a step back, but the step back is the step forward, because originally you were like the punch cards with the weavery, gave you a
See,
consistent
if
pattern.
you're a SQL coder, you wouldn't be surprised or bothered by that, because you can run the same code. If you don't have,
In SQL?
if you don't have an order by, your results can come out in different orders.
Right.
You'll get the same
right.
data, but it might be ordered differently, and that's just, there's no reason for it to be.
I have done a little bit of regression, and to me this feels like regression on steroids.
Like testing?
When you have the linear regression, you come up with an equation,
Yeah.
in machine learning,
Yeah,
you
it
have
largely
data, you
is.
train it, and then it builds a model, and then you can run it. It's a very simple model, and now here it's just too many parameters, and it's hard to understand.
What you described was, I believe it was added in the 80s, and that was the bias function, whereas the bias is going to offset the actuation function just by a little bit to keep it off of 0 and also to give it that little bit of flexibility in the neuron. So if you didn't have any bias, you would get the same output. But when you add in the bias feedback and you give just a little bit of adjustment, then there's wiggling. So this is what a modern LLM app architecture looks like right now. There's a lot going on in this. A lot of it's optional. A lot of it has a lot of different ways you can do it. But good, we have a cursor. Yeah. So your input goes in here into whatever is hosting your app. That's going to be, there's a whole stack of architecture right there. The orchestration, this refers to the actual orchestration of the models, how they're being loaded and handled and which ones. And this is, this graphic must be a few months old because it doesn't have model context protocol. And that's like the huge buzz right now is the debate over how to standardize models talking to other models. That all happens in here. In order to train anything, you need validated examples. You need some way to tell it it got it right or wrong. So you can create your examples over here and put that into the orchestration. You got plugins that might give you information. You can embed your context. This is called RAG, Retrieval Augmented Generation. That might come from a third-party pipeline. And then, of course, when you get into multi-agentic systems, you probably need one to get some results. You need another one to contextualize the results, validate it. You have different things that perform different functions. So it is enormously complicated at every layer, down to the functions that are being used in the hidden Markov layers, to the optimization of how the API is serving that model. There's just an enormous amount that goes into it.
If you wouldn't mind, can you talk a little bit on the embedding part? What do we do there?
So the embedding model is the LLM formula that you use to vectorize your information. So depending on which model you use, you can turn it into 1 billion parameters, 5 billion, 8 billion, like they're going up to 12, 32, like they're going way up. But you're going to
kind of like the formula your system relies on to generate the output.
Right. Yeah.
That's the embedding model.
It creates the matrix of the dimensions in which your data is fed into and positioned. So you put it into that vector space in a database, and then when you want to get better results for something specific, then you use an embedding model that is, this is what Ryan was asking about. You can use the embedding model to focus in on a certain subset of data. And then when you retrieve out of the database using the same model, then you can get the better results that you want.
So for example, I'm asking a question on, hey, tell me the health benefits of, let's say, some vitamin. So there is likely going to be, for example, an embedding model based on some healthcare data that can possibly, give me the results I'm looking for.
Yeah. Now, this is all in development so fast that GPT-4 comes out and they announce it's got medical data, it's got everything. Whatever you're looking for, it already has that. You can't build a better medical bot than GPT-4. But you could take it and make sure that it answers medically. So that's what fine tuning is for. It's if it's trained on everything, but I only want it to be a medical bot, then I not only instruct it in the context, you are a medical bot, answer like a medical professional, but also in the way that it retrieves answers, we want to tweak the whole weighting system to favor the medical interpretation of things.
So your model chooses an embedding, let's say I'm asking something, I have a query, I'm asking ChatGPT about it. So behind the scenes, it picks an embedding model based on my query. Can I say that?
No, the embedding model is something that we're adding in the architecture of using the chat model, or the multimodal chat model. So they're different models. And that's an example of the embedding model is only for interpreting data in a tokenized vector data space. It doesn't have image recognition, or it's not multimodal, it doesn't do any of that.
You keep saying multimodal. That means that it can do natural language and images and all that.
Trained on all,
multiple.
It can generate images, it can interpret images, it can speak different language, translate, fill in. And generally you will see the word, you see GPT because it's generative, it actually produces new tokens by predicting based on the pre-trained transformer.
But when we say GPT, as in the GPT model, we're talking about OpenAI, right?
Yeah, OpenAI was the one that released GPT, got it first, but it's not particularly different from the other GPT models. And GPT kit was a term before that.
Yeah.
So I talked about this. Wait, I already did that slide. So this is Ray Kurzweil. I've mentioned him a few times. And he said, we will merge with AI and augment ourselves with millions of times the computational power that our biology gave us. And this will expand our intelligence and consciousness so profoundly that it's difficult to comprehend. And he's saying this will happen within about 5 years. So in the industry, AI has sort of been taken over by AGI. And that has become the holy grail and the new term of what we're trying to do. We're not just doing AI because everything that I've talked about at some point here is in some way related to AI or a form of AI. It is artificial intelligence in some way. But AGI is the challenge of developing artificial general intelligence, where it doesn't have to be a robot, but the eyes see and the hands move, and it can think, it can learn, it can compute, it can do all of these things, and if we turn it into a streaming system, it might be conscious. Or we might be able to plug into it and just use its hardware so that we can think like that, and we can plug into other people thinking. Like I said, we don't know where this is going. And in conclusion, maybe we're all AI.
No, we're I.
We're OI. We're going to have to distinguish between AI and OI from now on. Organic intelligence, yeah.
That's how I have to remind myself.
So Anthony, I
Yes,
got curious and I asked ChatGPT what's the global power consumption of AI,
yeah.
and it said, gave a number, next year it should hit 1,000 terawatt hours, which this is roughly the energy consumption of Japan. So all of Japan's.
So we added one Japan's worth of consumption to the world, and that's growing
That's
like
significant.
every
That's
day.
significant.
We're not OI, we're high.
HI high,
High.
so high.
Human intelligence.
And another thing I heard is,
Human intelligence.
like on a motherboard, the wires are getting so close together that electrons can almost jump from one circuit trace to another.
Sometimes they do, yeah.
And so they're starting to investigate organic solutions for computing to make an organic microprocessor, essentially.
Oh, okay.
Which, so you're actually, then you pilot out on that and you build an organic brain. Make a digital computer
One that's,
out of
I feel like
organic.
they've
Like
been
algae molecules or something
researching that
that's
for
real consistent.
quite a long time now.
What's that, organic computing?
Yeah, some kind of, germs or
Yeah.
Are you,
bacteria or something.
so are you saying they are now looking at organic matter?
Right, because they can't make the circuit infinitely small or the electrons will jump from wire to wire. You have those exposed wires on your motherboard. There's a limit to how close they can be to each other.
but we also now have
Well, you can
quantum
make them as close
computing.
as you want.
It won't
might
work
not
anymore.
work.
It won't work anymore, yeah.
That's where quantum computing comes in, and we moved from 2 bits to like 4 bits, as I understand it, but not exactly, because it's
Oh, because there's more than two
it's
states.
like incomprehensible. Yeah, like it's not even 4 states, but it's
Even
more than
it's
2
qubits,
states.
right? I think it's even more, anything between 0 and 1.
There's
got two imaginary bits.
2 imaginary bits, in
I'm
addition
joking,
to
I
your
don't
real
know.
bits.
This is-
Yeah,
So you can take the square
right.
root.
Two theoretical bits with your 2 real bits.
There's this older German woman who's a quantum physicist. She has a YouTube channel. If you ever want to feel not real smart, listen to her for a while. I'm like, this lady's way up there. I'll get the name if you want. She's got a lot of different topics. She had an AI video she did that I was listening to. And she's talking about whether, like, habitating Mars was feasible, desirable.
The question is, should we make the monkey smarter?
Monkey what?
Should we make the monkey smarter?
Somebody might already be thinking of.
Actually, people are researching
Absolutely.
like
Just don't get
communication
them
interfaces
dots.
with animals. Like
Yeah.
based on their brain waves, how would you interpret this into language and like actually start like giving them some form of expression that humans can understand?
It's called uplifting.
We might be able to do that.
Flow state. So I wonder, is you're like an industry insider now. I've used generative AI on purpose for the first time on Friday.
Blasphemy.
Yes, thank you. So, but like, you hear a lot of stuff like, what's perceived like ethics problems and what's real. So I wonder what you think about that.
Fire this
What are
man.
some things that might be concerning or the future that might be concerning?
Well, we're all aware of the copyright issues and the way that a lot of these models were trained based off of data that didn't really belong to them, but they're profiting off of it.
And nobody can prove that either.
No one
They
can
weren't
prove
there
it.
when the training happened, yeah.
There's no way to enforce it. It's not possible. I mean, it's like the cat's out of the box there, so it is what it is.
Next it will take your soul.
But you know, that's not the first time that happened, because a college professor told me in the early 2000s, enjoy YouTube while you can, because it's gonna be gone soon, because copyright complaints.
Well, it has
Well,
definitely changed.
Google bought them and were able to fight through that, and, you know,
Well, I grew up in the 90s, and
they
of
didn't
course,
get shut down in 2004.
True, you go on there and it's
They
like,
survived.
you're like, you're scroll through YouTube, it just keeps regurgitating the same suggestions
Yeah.
over and over.
Does it?
Even if you try to search for something, it will mix it with.
Well, this is the bullshit I was talking to you guys about at the last meeting. It tries to silo you
Yeah.
into this little funnel of
So
boring.
there's
little
tons
train,
and tons
you
of
know?
content on
Yeah.
there. You will not find it via search, even
Really?
if it's publicly listed.
You will not find my YouTube videos.
So how do you find
you ask Perplexity to give you a good YouTube
it?
channel
Okay, good. I like that.
and then check out its
What
recommendations.
is
I
that?
know, it's like, so.
Perplexity is a multimodal
Oh,
or
I installed-
multi-agentic system.
I installed Perplexity during your talk today, so thanks for that.
Yeah, enjoy. It's amazing.
You
I have
talk
been
about
using a
complexity
range
in your
of
talk?
apps. I mean, they're very, very powerful.
What's
I
that?
use Grok from X. I
Oh,
use
okay.
ChatGPT at work,
Mhm.
and I have played around with Perplexity.
They need to make like.
They are getting better every single day.
They need to make like
Yeah.
a bug generating AI, like it intentionally generates like bugs.
Okay.
And then maybe it would do like good code instead, because like it'd be trying to give you a bug, and the bug would be to write good code.
Probably would.
Thank you for the presentation.
You're welcome.
It was
Thanks for
very
watching.
entertaining.
Maybe it just doesn't like it.
So
Can AI make
I wonder what
clones?
made
Yeah.
you, so you've been doing,
Let's try it.